So for the chemistry questions you will encounter, there are basically two types of setup you will see to work out the enthalpy change, usually for a reaction. The first one is this one, where a fuel is burnt and that raises the temperature of a substance, which is usually water. And then in the second situation is where the reactants themselves are placed into the container of water, and then the heat is generated within the container itself from the reactants, whether that causes the temperature to rise or fall. But it's a slightly different setup to this one here, which I would say this first one here is more straightforward. Before I get into the question, I'm going to go through the formulas and symbols in each formula, because in chemistry you tend to see this formula, Q equals mc delta T, and then in physics you see E equals mc delta T. And I just want to clear that the E is exactly the same as Q, and it just means the energy generated in the reaction, okay, which is measured in joules. For the purposes of this video, I'm just going to stick with E, and for the videos I will produce on the physics style questions, which I will link below, I'm going to use E as well, okay. Delta T is your temperature change, and that can be in degrees C or Kelvin, depends on the question. M, now this is very important, M is the mass of the substance being heated up, which in this case it is always the vast majority of the time water, okay. It's just not the substance that's being burnt, which I've just underlined in red, the methylbenzene, it's the water. So M is always the mass of the substance being heated up. And then finally we have C, which is the heat capacity, specific heat capacity. Now what the specific heat capacity is, I'll just say this really slowly, it's the energy required to raise 1 gram of that substance by 1 degree C or 1 Kelvin. Okay, the temperature, unit of temperature doesn't matter as long as you're consistent with it. So for water, that number is 4.18. So in other words, you need 4.18 joules to raise 1 gram of water by 1 degree C. So pretend this little bucket there represents 1 gram of water. To make that go up by 1 degree C, I need 4.18 joules. So first of all, let's work out the energy of this reaction. So we are burning methylbenzene, which is a really volatile hydrocarbon, kind of like petrol or diesel, very flammable, and the heat is being given off, goes into the water, and it heats it up. E equals mc delta T. So M is the mass of the water, which we can see is 250, not the mass of the methylbenzene. We need that for something later on. Remember, it's the substance that's being heated up, not the substance being burnt. So 250 times 4.18 times the temperature change, which is, tells us there, 60. So if we put that into the calculator, we get, so that is the energy supplied to the water during that combustion reaction. Right, that's the energy. That is not the same as enthalpy. Enthalpy, which I'm just writing here in black, has the symbol delta H. And basically what that is the energy per mole of the substance burnt, or per mole of the substance reacted. So whereas energy, E, is just measured in joules, it's just the energy of the reaction, enthalpy is always quoted per mole of the reactant or substance, whatever it is. Okay, so it must be per mole. So how do I work out the moles of the substance that is being burnt? Well, for that, I need to turn to the beginning part where it tells us that 2.5 grams of the methylbenzene was burnt. We have moles equals mass over RFM. The mass is of methylbenzene burnt is 2.5. The RFM stands for relative formula mass of methylbenzene, so that is C7H8. So it's going to be 7 times 12, because carbon has a atomic mass of 12, plus 8, gives us, okay, so 2.5 grams of methylbenzene is equivalent to 0.02717 moles. That's the number of moles that have been burnt during this reaction. Finally, how do we change this answer into an enthalpy change? Well, The clue is in the unit of enthalpy. It's energy per mole. So all you have to do to work out the enthalpy, I'll do this in red, it's the energy of the reaction divided by the number of moles of the reactant. So I just do 6 to 700 divided by 0.02717 gives 2307,692.308 joules per mole. Now, the standard unit for enthalpy change is actually kilojoules per mole. So what I have to do before finalizing my answer is I need to divide this by 1,000. So don't forget this step. So dividing that by 1,000 gives me 2307.7 kilojoules per mole when expressed to one decimal place. Finally, when considering the sign of the enthalpy change, this reaction is combustion. It's enthalpy of combustion, which means that it's exothermic. So you must remember to include a negative sign at the end, because enthalpy changes of combustion or negative enthalpy changes, which represent exothermic processes, must always carry a negative sign, whereas if a reaction is endothermic and the overall energy is positive, energy absorbed from the surroundings, then the enthalpy change will have a positive sign. So don't forget to check your final answer to make sure there's a negative sign attached to it. If it is a combustion reaction, which is obviously exothermic, you just know it to be an exothermic reaction. Right, so that's the first type of specific heat capacity question you will see in chemistry. The second one involves, if I just scroll up, instead of a fuel being burnt outside of the beaker of water and then that causing the temperature change, as I've illustrated here, the second style of question is where you have maybe two reactants A and B, and they are both put into the container of water, and then they generate the temperature change when they react together, whether they cause the temperature to increase, such as in many neutralization reactions, or whether they cause the temperature of the water to decrease. For example, dissolving certain salts is an endothermic process. So it's a different way of approaching the calculation compared to what I've just outlined here, and is what I have covered in the next video. So please go on to watch that now. The link is below the description to this one. So let's go.